Okay. All right, everybody, let's get started. Lecture 8. Okay. Just a couple of housekeeping items. Let me get the lights and whatnot. Okay. So a couple of housekeeping items. So I've got the attendance grades up to date on Blackboard. I've started to chip away a little bit at the backlog of homework. So homeworks 2.2 and 2.3 are graded. Still working on grading homework 2.4, but I'll probably knock out that and probably 3.1 this weekend. So so that way, come Monday, we'll be sort of caught up. How did the first Truss homework go? Well, hopefully the bookkeeping and whatnot was a little bit more straightforward. I'll tell you this. I've got a Truss for you today, due Monday, but it's a smaller Truss, okay? Not only is it a smaller Truss, but with the example that we're going to do in class today, we will be able to exploit symmetry, both on this example and the one on the homework. So that means we only have to analyze half of the Truss, not the whole thing. So that'll make life a little bit easier. Before we go down the rabbit hole of the lecture today, I know that some of you had a surprising reminder from your materials professor yesterday that you had an exam next week. So I just wanted to make sure and pull up the schedule here so everybody remembers that materials guy. I can't stand that guy. Okay, so all right. So just a little bit on the schedule today. So today we're going to go through and do another Truss example, but I'm going to take a little bit of time off to the side and discuss internal stability and determinacy. Sort of like the stuff we did in week 1, but just focused on trusses. One thing I do want to say on Monday, make sure and bring your calculator on Mondays, and I mean it specifically, your Casio or any scientific or graphing calculator, because what we're going to do on Monday is we're going to do a particular type of joint analysis that is a little bit easier if you can solve a 2x2 system of equations. And so most scientific or graphing calculators can do that automatically, and so it's nice to have one. The lecture on Monday also is going to be a nice little refresher on matrix algebra, which is going to be important a little bit later in the semester when we start doing computer analysis of structures, because that's how computers analyze structures, is all through matrix methods. So that's what we'll do on Monday, and we'll also look at zero force members on Monday. But higher level, so we're doing Truss analysis today and through next week. At the end of next week and beginning of the following week, we're going to start looking at structural deformations or deflections. So we'll start that topic by looking at trusses. So the way I teach structural analysis, I do all the truss stuff, then all the beam stuff. So what we'll do is next week and then a little bit of the week after, on Monday, September 15th, that'll be the last day we discuss deflections and trusses. Then what we're going to do is that Wednesday, I'm going to introduce the analysis project for the class. We'll have a day discussing that. We'll review the exam, or for the exam on Friday, and we have our celebration of learning Monday, September 22nd. So I'm telling you this now so that it's not a surprise. Okay. Okay. Does anybody have any questions just about housekeeping moving forward? Everybody good? Okay. And then one more time, did everybody get the code?
Come on, man.
Hey, stop. There were others, by the way. So.
I couldn't see them.
Okay, everybody get the code? All right. Okay. So, all right, so let's just sort of recap where we left off last time and then sort of dig into things a little bit more today. So in the previous lecture, we discussed trusses as a whole, and we went through the 3 assumptions that we make when analyzing trusses. The idea that we assume that there is no friction at the joints where truss members are connected. We assume that all of the loads are applied directly at the joints, including the support reactions, and that we also fabricate trusses such that the centroidal axes, the neutral axes of all the members, all coincide at the intersection where the joint is. And what those assumptions essentially mean is that truss members carry only axial force. That's what those assumptions are gearing towards. So we basically are assessing whether or not a member has tension or compression, okay? Now, we haven't had an in-class example with this yet, but it is possible, and we'll talk about this more on Monday, that you could have a truss member that carries a certain amount of tension, a certain amount of compression, or it could carry nothing. It could be a zero force member and it has no force in it at all. We'll talk about that a little bit more in detail on Monday as to what zero force members are and why they are even there in the first place, because I'm sure that's a question bubbling in the back of your head, is why put a member in a truss that doesn't carry any load? That's a good question. We'll talk about that on Monday. All right. We have two methods that we're going to analyze trusses with. We've already explored the method of joints, so we're going to do that more today. And again, the method of joints is really what I like to focus on in this course. We'll do the method of sections next week. Now, the big thing I wanted to make sure we're all clear about is that when we employ the method of joints, we are limited to assessing a joint that has at most two unknowns. Now, why is that? Why can't we start with a joint that has 4 or 5 members framing into it, 4 or 5 unknowns? Why are we limited to joints with 2 unknowns? We have 2 equations of equilibrium. We don't have 3, right? Because at joints there are no moments. The only thing we have is the sum of forces in the x direction and the sum of the forces in the y direction. Okay. All right. Okay. All right. Okay. let's talk about indeterminacy though, because this is something that we didn't really talk about last time, and we just sort of barreled through with a truss problem, which I think is a really good way to start this section in this course, because you've already seen trusses, and so the last lecture was really just sort of a shake the rust off sort of exercise. Today I want to talk about trusses in a little bit more meaningful way. Okay, so I want to go back to what we had discussed in week 1, and we had discussed indeterminacy and stability. Okay, so let's go back to that discussion, and if you recall, we had this equation where we can compute the degree of external indeterminacy. And the equation is fairly plug and chug. We take the quantity R minus the quantity EC plus 3, R being the number of support reactions, and E sub C being the total number of equations of conditions, right? And then what we said is that if I sub E, if it's negative, the structure is unstable. We said that if it's non-negative, either 0 or positive, that the structure should be stable, should be stable. If the value is 0, it should be statically determinate. If it's greater than 0, it should be statically indeterminate. And remember, that whole should be was that there are qualifiers to this determination, because the reactions cannot all be concurrent, and they cannot all be parallel, right? Because remember, if you had a beam that had 6 or 7 roller supports, you're going to get a positive value of I, but it's essentially a skateboard. You apply a lateral load, it freely displaces, and it does not resist that, right? We've already done this a while back, so this is all should be relatively familiar. Everybody good with this? Okay. Now, I mentioned this last time, that I didn't say that this was the degree of indeterminacy. I said it's the degree of external indeterminacy. Okay? What we were looking at with this expression is we're basically just looking at the structure as a whole and asking ourselves, can we compute the support reactions using solely the equations of statics, or do we need other information? And that's where indeterminate analysis comes, which we'll talk about later this semester. But we're only looking at the external support reactions. What about the inside of the structure? What about the internal forces inside the members? Okay, so let's take a look at this truss. Okay, so I picked this truss for a very specific reason. Okay, so I have a truss. It has a pin support and it has a roller support. Okay, all right. So let's keep that in mind: pin support and roller support. So what can you tell me about this from an external indeterminacy standpoint? Is this structure unstable? Is it indeterminate? Is it determinate? What's the deal there? From what we did like a couple weeks ago, how would you classify this structure? Well, let's start off. Is it stable? Yes, it's stable. Okay. Is it externally? Is it determinate? Is it indeterminate? What's the deal? Like if I put a bunch of loads on there, can I compute the reactions? Yes, okay? It is, we can very easily compute the reactions. So I propose externally, this structure is stable and statically determinate, okay? That's fine. The problem comes when we try and determine the internal forces in the structure, okay? How many unknowns are at this joint right here? 3, right? Because there's 1, 2, 3. How about this one? 3. This one's got 5. This one's got 5. Are there any joints in this structure that have 2 unknowns? No, there aren't, okay? So the problem is that this structure is determinate externally, but internally it's not, okay? I can solve for the reactions just fine, but once I start getting into the method of joints, I'm going to have a problem, okay? I'm not going to be able to solve the internal forces because of this. Okay, so I propose that this truss is indeterminate internally, okay? That internally there are too many unknowns in order to solve the internal forces in the system. And remember, what is indeterminacy? I mean, we had this formula before. We had this I sub E, and we said it was R minus E sub C plus 3. Okay? But really, if you recall, this was just a fancy way of comparing the unknowns to the knowns. Okay? Remember when we were looking at external indeterminacy, we said, what are our unknowns? Well, they're the support reactions, right? So however many support reactions there are in the structure, those are our unknowns, okay? What about the knowns? What are the known quantities? Well, anytime we have an internal hinge or an internal release, we know what the response is inside, but why the number 3? Why do we have the number 3?
3 equations.
We have 3 equations of equilibrium externally. We have the sum of the forces in the x direction being 0, the sum of the forces in the y direction being 0, and the sum of the moments about any arbitrary point equal to 0. So what that meant is that for any structure, we have 3 facts that we know by default, and then we might know more if we have internal releases. Okay? Does that make sense? Okay. What I'm saying is that when we're looking internally at trusses, we can kind of make the same comparison, or the same distinction, if you will. So let's talk about unknowns and knowns, okay? And let's think about this from a method of joints perspective, okay? How many joints are in this truss right up here? How many? 1, 2, 3, 4, 5, 6, 7, 9, 10, right? There's 10 joints, okay? So let's ignore how many members are in each joint, but let's just say there are 10 joints. When we perform a method of joints analysis, we investigate the equilibrium at each joint, right? Okay? Now, for each joint, how many equations of equilibrium can we apply? 2, okay? So let's think about it like this, okay? Let's now see, if we can figure out, let's see if we can derive maybe an equation for I sub t, a truss indeterminacy, okay? So we've got the number of unknowns minus the number of knowns. So let's start with the knowns first. So I propose for every joint, there are 2 known facts about each joint, right? We know that the sum of the forces in the x direction must be 0, the sum of the forces in the y direction must be 0. So could I characterize my knowns as 2j? And again, why is it 2 and not 3? Because for joints, there are no moments, right? Does that make sense? That internally, that's the deal that's going on, okay? Now, what about unknowns, okay? When you perform a truss analysis, what are you trying to determine? Like if I give you a truss and I say, analyze this truss using the method of joints, what am I asking for? I mean, what am I asking? Like if I gave you this truss and I say solve this truss, what am I asking for member AH? What am I asking for member AB? The tension or compression, right? So how many unknown quantities are there for every member? There's 1, right? Remember, trusses carry only axial force, okay? So I propose for every member in the truss, there's an unknown, right? So there's an unknown for every member in the truss, okay? And I'm also going to tack on the reactions as well, because those are unknowns regarding the forces on the joints as well, okay? So what are my known quantities? Two equations of equilibrium at each joint. What are my unknowns? Well, there's an unknown for each member in the truss, and there's unknowns for every support reaction. So I can very easily compute an internal degree of indeterminacy very easily by just saying that the internal indeterminacy is m plus r minus 2j, okay? And it's, again, what am I comparing? The unknowns to the knowns, okay? So let's just think this through. What happens if I sub t equals 0? That means that I can solve the truss using statics, and that's it, right? If I sub t is bigger than 0, that means I need something more than statics. That means the structure is indeterminate, okay? And again, the same idea before. If I have I sub t less than 0, we'll consider that structure internally unstable, okay? Does that make sense? Same idea, okay? Now, the same caveat applies, the whole if I sub t is 0, it should be stable. If I sub t is greater than 0, it should be stable. There's the same caveats there. So when I say should be, first off, for a truss to be internally stable, it's got to be externally stable, okay? Again, I don't really care what the internal stability is. If the external stability isn't there, it doesn't matter. The structure is unstable. But really, the biggest note on should be is that regardless of what you calculate for I sub t, the truss has to be constrained against what we call rigid body movements. And basically what that means is if you ever have any region in a truss that has a big old open box like that, that tends to mean instability. And we don't really build trusses like this anyways, so it's not really a chief concern in most instances. One thing I will say is that this can be a little difficult to view visually, but ironically it's very easy for a computer to determine whether a truss has an internal instability. If you ever build a computer model of a truss and you get an error because of stability, it's because it's checking stuff like that. And we'll talk about how how software packages do that a little bit later in the semester. Okay. Everybody with me so far? Okay, so this is a very plug-and-chug expression. I'm going to give you a couple problems on this. Today, what I want to focus on is just another truss example. I'll say this. So this is the truss example that I'm going to do. I went ahead and did this computation for I sub t right here. So how do you do it? Well, let's see. How many joints are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 joints. There's 3 reactions, 1, 2, 3. And as for the number of members, just count them, okay? So I'll count on the left half of the truss. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, and then the vertical member makes 21. So there's 21 members in the truss, 3 reactions, 12 joints. So m plus r is 24. 2 times 12 is 24. So the structure is stable and statically determinate. Okay, does that make sense? I'm hoping that's pretty straightforward, that I'm not reinventing the wheel with that one. Sound good? Now, a couple things I want to point out, and really this is the two things I really want to focus on with this example. Okay, point number 1, this truss is symmetric, okay? It's symmetric with respect to both geometry and the loads. We didn't have this last time, we have today, okay? Structural engineers do their best to try and exploit symmetry whenever they can, and in this case, this is definitely happening here. It gives us a benefit as analysts because we only have to analyze half the truss. For example, if I calculate the force in member AB, I automatically have the force in member FG. If I calculate the force in member HI, I automatically have the force in member KL. In other words, it's symmetric. with respect to this, so just fold. Okay? So if you notice here on the board, I've only drawn this half of the truss because this is all I'm going to analyze. Once we get to this member, we're done. Okay? And the results are symmetric. Is everybody okay with that? Okay. So that's point one. The second point is that the truss that we did last time and the truss that you did on the homework assignment, the members all had the same slope ratio. That is not the case with this problem, okay? So we need to be careful with our bookkeeping, okay? So what I've got here is the truss drawn here, and I've got all these empty slope ratios. Let's just see if we can fill those in right now, okay? So let's start off with AH. So AH, we go over 12, up 6. Does everybody see that? So that means this is going to be a 1 to 2. Is that okay? All right. So if that's the case, tell me what's going on with HI. You tell me. I'm going to make you all work this morning. 1 to 2. What about IJ? 1 to 2. Okay. What about BI? What's the deal there?
1 to 1.
That's 1 to 1, right? Because we're going over 12 and up 12. Okay. And then finally, what's the deal with CJ? We're going over 12 up what? 18. So 12 and 18, what is that? 2 and 3? Is that, you tell me, I do that right? Okay, so honestly, this matters more than the dimensions of the truss, because when we resolve this to be a method of joints analysis, that's what we're going to focus on. Okay. All right, before we start barreling down the road with this analysis, do you remember last time how we said we were going to develop sort of an order in which we solve the structure? Let's do that now. Let's do that right off the bat. Okay? So, which joints should we solve first? A. Okay, because there's 2 unknowns. Okay? Now, that's going to give us this member and that member. Okay? So after I solve joint A, what should be the next joint? H, right? So I can't solve B because if I have this member, that's great, but I got 1, 2, 3, so we'll solve H next. Okay? And once we solve H, what's that going to give us? It's going to give us that, right? Okay, then what? B. Everybody good with that? Okay, so that'll give us that member. Now what? I. Okay. Now what? Maybe C. Now, let me ask you a question. So, we have, this truss is symmetric, so we've got this member too, but I'm lazy. So which joint do you want to solve last, J or D? You want to solve J? I wouldn't if it was me, because you've got 1, 2, 3, 4, 5 members framing through J.
Oh, last?
Yes.
That's what,
Well, what I'm saying is, could we solve D?
yeah.
Like, I would solve D, is what I'm getting at, because there's a lot less going on. I'm lazy, is what I'm getting at. You'll see what I mean when we get there. Okay. All right. So now instead of scrolling up and down, I've got this here. Let's just jump right into it. And today, I want to be clear, you all are going to be helping me do this, okay? So I need your help a lot more today than last time. Okay. So joint A. Okay. First off, let's draw our members. So joint A has 1, 2 members, 1, 2 members. Are there any loads passing through J? Or sorry, through A?
Yeah.
Okay, what's the load?
15 kids.
Okay. So that means we've got unknowns to solve for. So we have a diagonal. So I'm just going to draw myself a line like that. And a line like that. And a line like that. So we'll call this, what is that? AH. So we'll call this AH, Y, AHX. And call this line AB. Okay. All right. I need help. My coffee hasn't kicked in. You tell me what to do. Somebody tell me what to do.
Some forces in the Y.
Let's sum forces in the Y direction. Okay. So if I sum forces in the Y direction, that tells me what?
AHY is 15 kips going down, I think.
Do I have a second on that?
Yeah.
Okay. Okay, so you drew that down and got that 15 kips. Okay. Somebody over here tell me what to do. Again, my coffee, they must have given me decaf because I'm not awake enough to do this problem. I need your help. Tell me what to do. Use the slope ratio. Okay. So so the slope ratio, if I know AHY, that's going to tell me what AHX is. Okay? So how am I going to compute AHX given AHY? What am I going to do? It's going to be times 2, right? Because the horizontal component's got to be bigger. So the question is, do you multiply it by 1/2 or do you multiply it by 2/1? And you're going to multiply it by 2/1 because the horizontal component has to be bigger. So it's going to be 30 kips. Now, which direction does that point? To the left. Okay. So that's AHX. Now what? Summon forces in the X direction. That'll give me AB, and that's what?
30 kips going to the right.
30 kips going to the right.
Or in tension.
And that's going to be the next point. Exactly right. So, okay. So sort of the first step in the joint analysis is to just find our components and their directions, which we've done that. Now let's see if we can conclude what's going on with our analysis. Okay? So that means we've identified member AB, and we've got member AH. Those are the two true unknowns. Okay. Now you had said this is 30 kips, and you said that was 30 kips in tensions. Everybody agree with that? Okay. Now what about AH? How do I get AH? Pythagorean theorem. So what is that, by the way? Like you brought your Casio FX 115 as plus or similar sign.
33.54.
I know, I need that. I say it so often. What is that, by the way?
33.54.
33.54. Do I have a second?
Yeah.
Okay, and is that in tension or compression?
Compression.
Oh, which is it?
Compression.
Compression.
A compression. Okay. Now, I do strongly recommend whenever you do method of joints, like I think one of the biggest challenges with the method of joints problem or a truss analysis in general is just all the bookkeeping. So I generally think it's a good idea. See, like over here, this is like where I'm doing the joint analysis, and then on a separate sheet of paper, I've got the whole truss drawn, and then as I solve the truss, let's say this and this. In other words, like I'm writing down the answers on the problem as I'm doing it. You see that? So it helps you with bookkeeping as you're doing the problem. And then when you're done, this diagram, this is your answer. Okay? So let's keep going. And then again, I like doing it this way because, see, we've already done this. We don't have to decide which joint we're going to do next. We've already identified we're going to do joint H next, right? Okay. Everybody good so far? Sure. Okay. All right. Okay. So remember when we're doing a joint analysis, so the first thing that we do is we identify the members, okay? So joint H, I mean, what does joint H look like? We've got a member here, member down, right? So it's going to look something about like this. Wow, let's do them here. So there's our joint, okay? Slope ratios. So here's joint H. We have a 1 to 2 and a 1 to 2. Okay. Now let's do our knowns next. Are there any loads applied to joint H?
Yes. 6 kips going down.
6 kips going down. Okay. And then, now we chose joint H because, well, I mean, I don't know about you, it looks like I've got 3 members, but I already know one of them, don't I? I know this one, okay? So this one is, I know the X and Y components for this right here. I know this one. Okay, so is this member tension or compression? Compression. Okay, so how do I draw the arrows?
Up and to the right.
Up and to the right, okay? Okay, and this one, this vertical one was, what was this component?
15 kips.
15, and this one was?
30.
30. And we've got that, that, that. So we'll call this HI, Y, HI, X, BH. So again, so the thing about joint analyses is it's just, you know, the further you go into the structure, just a little bit more bookkeeping. Okay. So again, my coffee, it's not kicking in. So what do I do?
Sum the forces in the X.
Sum the forces in the X direction. Okay. So okay. All right, so tell me what to do. Tell me what does this mean? Like why sum forces in the X direction? What were we trying to solve for?
HIX.
HIX, and HIX is going to be what?
30 kips to the left.
Do we agree with that? They do. I got a lot. All right. So now what?
Turned up.
Now what? Somebody up front. What do I do?
Just slope ratio to get HIY.
All right. Okay. And it's going to be what compared to HIX?
Is it double or 1/2?
I'm asking you. Now hold on. So let's talk this through, okay? So whenever you're trying to figure this out, this is a great time to explore this, okay? The answer to these questions is always just reflective here, okay? So it's either going to be 2/1 or 1/2. Do we all agree with that? It's either going to be 2/1 or 1/2. What are we solving for? We're solving for the vertical component, right? The vertical component is the smaller number. So this answer needs to be smaller than its counterpart, not bigger. Okay? Does that make sense? Everybody okay with that? Okay. So just think it through that way. Like what? Okay. At the end of the day, if this is 30, this has to be 15 because 30 is to 15 as 2 is to 1. Okay? So this is 15 kips, but which way?
Down.
Down. We in agreement? Okay. So, okay. So now what?
BH, also some forces in the line.
Some forces in the Y. Now here's what I'm going to do, okay? Because there's a lot more going on with this joint than there has been in other ones, I'm going to be a little bit more formal with this and say, let's draw our little table and let's put everything going up and everything going down. Let's just sort of document it to see what we've got here, okay? So, do I need to consider the 30 kips? Do I need to consider the 15? So let's put this here. Okay, what about the 6 kips? It's going to go right here. I'm going to put HIY right here, but that's 15 kips. So BH, does it need to act up or down?
Up.
Up. So we'll put BH right there. Draw that like that. And so we're getting BH plus 15 kips is 15 plus 6 is 21. Like that. Okay? Is that okay? So there's no problem with going through and doing it formally. And I mean, think about it. Like, what if we were doing, I don't know, like joint J? I mean, there's like 5 members framing into joint J. So, yeah, break out the table. There's nothing wrong with that, okay? So far, the joints have been pretty straightforward, but there's a lot going on. Document it. Okay. I'm going to smooth this over here. Okay. So, to summarize, we have 2 unknowns. BH, so that one was 6 kips. Is that compression or tension? Compression. This is, oh, I got ahead of myself. Okay, so what is this?
33.54.
Same thing, okay? Bless you. And that's also in compression, right?
Yes.
Okay, making sure. All right, so Okay, all right, I want to point something out. I want everybody to pay attention here, because this is a sort of separate discussion I want to have about this joint. Are these two members what I would call collinear? They're along the same line. Okay? And notice how they both have the same force going on. Let me ask you a question. If we were doing this joint analysis at joint H, what would happen if that was gone? Let's think this through. I guess my big question is, what would the force in this member right here be? 0. Interesting. So if we have these two members along the same line, and this load was gone, that'd be 0. Keep that in mind for Monday, because we're going to use this as a trick to identify some zero force members. It'll be pretty nifty when we look at this on Monday, because I'm going to give you a truss, and you'll be able to sort of eyeball the truss and solve half the truss without doing any math. So it's a nifty little trick. So, okay, keep that in mind. All right. So next up, joint B. Okay, and we probably won't finish the entire truss in here just for time, but we now have our strategy. So one thing I'll say is, when it comes to a truss analysis, if you get to the point where you're doing a problem like this and you understand what you're doing, and it may even get a little boring, from my perspective, that's a good thing, because that means you understand what you're doing, and it's like you learned something. It's like I'm interested in that, you all learning stuff, you know. Yeah, it's like I'm a teacher or something.
Doctor, actually.
Funny guy. Got jokes. Okay. Okay. All right, so this is our joint, okay? This is our joint. Now, okay. All right, hold on. This is 1 to 2, right?
No.
Mr. Wheeler's shaking his head no, right? Because it's not. What is it? It's 1 to 1. Okay. So this is what I meant when I said, like, this is another value of just having the truss drawn over here. Like, I mean it. Have like a sheet of paper over here with the truss and a sheet of paper over here where you're doing the joint analysis. So you just have something to look at when you're doing it. This can help resolve so many mistakes. I find that when I'm grading truss work, it's not that students don't understand it. It's that they accidentally made this a 2. And something as simple as accidentally making this a 2 makes this joint wrong, which if this joint's wrong, you're going to take that force and bring it up here, and then you're going to take that force and bring it down here, and the whole thing's going to be wrong, right? It's a bookkeeping challenge more than it is some mathematical exercise, okay? So again, I find that to be very important. Okay. Are there any loads, external loads applied to joint B? No. And again, why is that so easy to determine? Because you got a picture of the truss right there. Are there any members that we know?
Yes.
Okay, which ones?
I'll not tell you.
That was good. I'll give you that one. But I'm going to remember that. So. All right. Seriously, which ones do we know? Do we know this one? Okay. 30 kips. Which way do I draw the arrow?
To the right.
Oh, wait a minute. Hold on. Hold on. We got a conflict here. So this member is in tension. Okay? So if I apply a force to this joint in tension, what is tension? Tension is yanking, it's stretching. How do I apply this force in tension? To the left, away from the joint. Okay? Okay, I don't know what happened there. Okay, does that make sense? Okay, because again, what's that?
I said, I suppose.
Well, so again, like, if here's this chord, right? Okay, so look right here. If I have a cable, right, and I want to apply tension, what do I do with my hands? They go in opposite directions. This hand goes that way, this hand goes this way, okay? So when we did the analysis at joint A, we found that AB was going to the right. So when we go to the other joint, the force goes to the left, okay? Equal and opposite, all right? Does that make sense? Does that make sense?
Yeah.
Okay. So, all right, then help me out. We know this vertical one, right? We know that it's 6 kips. Which way do I draw the arrow?
Down.
Down. Okay. All right. Let's see if we can knock this joint out real quick, and then we'll probably call it with this one. Okay. All right, so help me out. We've got an unknown here. Unknown here. Unknown here. So this is BC. This is BIX, BIY. Okay. Is my schematic complete? It's not? Am I missing something? Am I? I think it's complete, because here's the joint. We've got a member. 1, 2, 3, 4. We know these two. I think we're good. All right, so tell me what to do. What do I do? Somebody over here.
You got this, buddy.
Yeah, help me out. What do I do?
It's always me.
Well, it hasn't been you all day.
No, dealing with him.
I can't do
I
anything.
can't believe I actually thought he wasn't going to say something stupid today. Can you believe that?
Stop.
That's on you.
Stop.
Yeah, it is on me.
Tell me what to do.
We would sum the forces in the x direction.
Stop. Seriously. Now, hold on.
That was fair. I'll get that one.
No, it wasn't. No, it wasn't. Now, okay, so let's talk this through. Seriously. Let's talk this through. Okay, how many unknowns do you have in the horizontal direction?
2, I didn't see BC.
You have 1 in the y, right? So deal with so if we sum, let's think this through. Now this is important because when you're doing a homework problem, it's very easy that you do this and then you get stuck, right? So summing forces in the x direction means you would get this plus this equals 30 kips, and it wouldn't isolate one. Summing forces in the y direction, we can isolate BIY. Does that make sense? This is important, okay? So if we sum forces in the y direction, so what does that give me? BIY is what?
6 kips going up.
6 kips going up. So now what? BIX, right? And if this is 6 kips, what's BIX going to be?
6.
6, because it's a 1-to-1 slip ratio, right? So that's easy, right? Which direction?
To the right.
To the right. Do I have agreement? Okay. All right. I'm going to need some help from this middle part of the room. So tell me what to do next. What is BC going to be? 24. Okay. So to clarify, let's put our arrows here. Okay. So we have 30 going to the left. We have 6 going to the right. So you're saying we need 24. And which direction? What was that?
Right.
The right. Everybody in agreement? Good. Okay. So, just real quick, BC is going to be 24 kips in what?
Tension.
Tension. And then BI, we'll do our Pythagorean theorem. And we're running short on time, so we can't do any more right now.
Is it 8.49 kips in tension?
Do I have a second?
Yeah.
There we go. Okay. So, we now have this member and this member. Is everybody getting the gist? Okay, that's sort of the point, okay? So you can keep on chugging along. I'm giving you a problem, a homework problem. The Truss is somewhat similar to this. I've also given you 2 internal classifications, so they're pretty easy. That's due Monday. Monday, again, bring your calculators for 2x2 matrix solution. That's all I got, everybody. Y'all have a wonderful weekend. Give me one second.